Hello, dear students. Welcome you all. Students, in today's lecture, we are going to discuss the next application of Maxwell thermodynamic relations, and it is uh, regarding the energy equations. Energy equations. Right? We will drive first energy equation and second energy equation. You will see what are these energy equations. So first of all, we are driving the first energy equation. Clear? That will tell us about the change in internal energy with volume. Right? So first of all, we will drive first energy equation. Right? That equation will then tell us about the change in internal energy with volume in case of ideal gas and then in case of real gas. Clear? So first of all, we will drive the energy equation. We know from the first law of thermodynamics, dq is equal to du plus pdv. Clear? Second law of thermodynamics, dq is equal to tds. So from this to this, I got tds is equal to du plus pdv. Clear? I can write it in the more simplified form. ds is equal to du plus p dv upon t. Clear? Uh, let this is equation number 1. Clear? Now we know from the Maxwell second equation, curly s upon curly p at constant temperature, that is equal to curly p upon curly t at constant volume. Clear? So now here we have written ds is equal to, I can take it curly s and put this in equation number 3. Then what it will become? It will become here, in that case, it will become 1 upon T. I'm taking it outside because the temperature is constant. Curly upon curly B. What is ds? It is du plus pdb upon T. Clear? Right. At constant temperature. That is equal to curly P upon curly T at constant volume. Clear? So what will be the effect on this equation number 3 when we convert it into this equation? Then it will get 1 upon T, right? Here I have mistaken. What I have mistaken? It was curly S. So it will not be curly here. This was the mistake. We should take into consideration. Right. So it becomes, in that case, I can write it 1 upon curly. It will become then curly U upon curly B at constant temperature. Curly V, curly, I can take it curly V also and it curly U also, because we have taken here curly S. So in that case, when we are write here partial derivative curly S, curly U, curly B, right? So then it will become plus curly b will get cancelled. You will get uh, p upon t, p upon t, that is equal to curly p upon curly t b, right? Now if I multiply by t on both the sides, then this equation will get converted into what I did. I multiplied by t on both the sides. Clear? This let this is equation number 4. Now I can convert this equation further, then modifying it, it will become curly u upon curly b at constant temperature, that is equal to t curly p upon curly t b minus b, right? Now this equation, let it is equation number 5. It is called a first energy equation. Energy, what this equation is telling us? This equation is telling us about the change in internal energy with change in volume at constant temperature, right? So I have told you in the beginning that we are actually looking at the change in internal energy with change in volume, but we are now taking the case of ideal gas and real gas. So let's take the first situation for ideal gas. What is the ideal gas? Ideal gas is that gas which obey all gas laws, right? Uh, that gas is ideal gas, and for that gas we have equation PV is equal to nRT. So if we take N is equal to 1 mole, then PV is equal to RT. So P is equal to RT upon B. Clear? Now differentiating with respect to T. Clear? At constant volume, it will get curly P upon curly T at constant volume, volume is kept constant, that is equal to R upon B from this equation. Clear? I have differentiated this equation, so I got this. Now I'm going to put this value where? In this equation. Clear? In first energy equation. So that will give me curly U upon curly B T, that is equal to T multiplied by curly P upon curly T is R upon B minus P. Clear? So it becomes, what it becomes? RT upon B minus P. So what is RT in case of ideal gas? RT is PV. PV, B got B, it is PV upon B minus P. P minus P 0. So it means in case of ideal gas, curly U upon curly B at constant temperature is equal to 0. So when we are taking the case of ideal gas, then the change in internal energy with change in volume at constant temperature is equal to 0 when the gas is ideal gas, right? Uh, this was the first case. Now let's take the second case. The second case is a real gas. We know what are real gases. So in case of real gases, the gas equation is P plus A upon B square into B minus B is equal to RT, right? So from here we got P is equal to RT upon B minus B minus A upon B square. Clear? This was the real gas equation for the case when we have taken N is equal to 1. It's 1 mole. So let this is in this case this is equation number 1 for the cases of real gas. So again differentiating this equation 2 with respect to T and keeping volume V as a constant. So curly P upon curly T constant volume is equal to what it will become, R upon B minus B. This term differentiation will become 0 because it is a constant in this case. Now I'm going to put this value in a first energy equation, this equation. Clear? So it was T into curly U upon curly B at constant temperature is equal to T into curly P upon curly T B minus B. This was what? This was the first energy equation, right? So now this is what? Right? We are going to put the value here. So it will become T into R upon B minus B minus P. P is what? P is RT upon so it is RP is equal to RT upon B minus B plus A upon B square. What I did, I put the value of P. P is RT upon B minus B minus A upon B square. So here minus minus will become plus. So now these two terms got cancelled out. So I got curly U upon curly B temperature T constant is equal to A upon B square. So it means in case of real gas, the change in internal energy with change in volume at constant temperature, it is not equal to 0. It means it depend upon the uh, it depend upon these two factors, right? It is not 0 as it was 0 in case of ideal gas. So in real gases, it depend upon the volume at constant temperature, right? A is a constant, B is the volume, right? So this was the case of first energy equation, right? Similarly, we can drive the second energy equation also, right? So let's take the second energy equation case. Now, second energy equation basically deals with the change in internal energy U with the pressure. Clear? So, for it, again, we will start with the first law of thermodynamics. dq is equal to du plus pdb and dq is equal to tds. This is second law of thermodynamics. So again the same thing, curly s is equal to or we will put this tds here. So again we will get the same thing as we did in the earlier case, curly u plus p curly b upon t, right? So now this is the same thing that we have did earlier. I simply put TDS here, then I took T toward this side. DS is equal to DU plus pdv upon t, then I convert it into a partial derivative. Now this, now we are going to make the use of Maxwell's fourth relation. Right. We know Maxwell fourth relation, curly s upon curly p t is equal to minus curly b upon curly t p. Clear? So now we are going to make the substitution here. Uh, so now we are going to put the value of curly s here in this equation, right? Like this is equation number 2, right? So what it will become? The same thing, 1 upon t curly u plus p curly b upon curly p temperature T constant is equal to minus curly V upon curly T at constant pressure. Okay. Equation number 3. So when I will simplify this equation, it will, I am taking T toward this side. So it will become curly U upon curly P at constant temperature, right? Plus P curly B upon curly P, right? At constant temperature, that is equal to minus T curly B upon curly T at constant pressure. Okay, this is equation number 4, right? So now we have converted this equation into this curly U upon curly P, then curly B upon curly P at constant temperature. This is both these equations. Now this is equal to this. So if I rearrange this equation, then it will give me curly U upon curly P at constant temperature, that is equal to minus T curly B upon curly T at constant pressure minus uh, pressure B curly B upon curly P constant temperature. I took this term toward this side. So now this is the required expression, equation number 5. It is the required expression for change in internal energy with change in pressure at constant temperature T. Clear? This equation is called second energy equation, right? So by taking the help of this equation, we can now calculate the two different situations, that the situation of a ideal gas and the situation of a real gas. So this is all about these energy equations, first energy equation and second energy equation. First energy equation deals with the problem when the change in internal energy is with change in volume, and the second energy equation deal with the problem when the change in internal energy is with change in pressure. In the first case, we make the use of second law of second equation of Maxwell, whereas in this case we use the fourth equation of Maxwell, right? So this is all about this lecture. Now we have completed this topic also. So thank you very much.